Okay, now members, what we are going to consider, we are still in the conducting particles which are on planes, which are rough. But now, specifically now we are handling double inclined planes. Here, let us go through this one and see. A smooth plane and a rough plane. Now this one is having, it has a smooth and then a rough one. So, let us name it. So let us call this one our smooth. So this one is smooth. And then we shall call this one a rough one. A rough. Okay, both inclined at 45 degrees to the horizontal. So both 45 degrees to the horizontal. Even this is 45 degrees to the horizontal. Intersect at a fixed point. Horizontal reed. That's inclined, they are intersecting at this. So, of course, if this is 45 and this is 45, you don't need to be told that is going to be 90 degrees, like that. Okay, a particle P of mass 1 kilogram is held on a smooth plane. Particle of mass 1 kilogram. So this one of mass 1 kilogram. So this one is 1 kilogram. Is held by a light inextensible string which passes over a smooth pulley at A. So this one, of course, at this edge, we are going to be having a pulley which passes over pulley A and is attached to a particle Q of mass 3 kilograms which rests on a rough plane. Okay, so this particle is going to be connected by a string which passes over a pulley, and then it's going to be connected to a particle here which is going to be having 3 kilograms. Okay, after doing that, this is our pulley. Okay. The plane containing P, Q, and A are perpendicular to the ridge. I think we can see they are perpendicular to the ridge. The system is released from rest with the string taut. Given that the acceleration of the particles is root 2 meters per second, find the tension in the string coefficient between Q and the rough plane, then the magnitude and direction of the force exerted by the string on the pulley. Okay, so that's what we have basically in our sketch. This one is smooth, so we don't expect friction, but this one is rough, so we expect their friction. Of course, for every weight, we first resolve this one. This will be now 1D, because 1 times the gravity. Then this one is going to be 3, the mass, then times the gravity. So we have resolved, we have put away. So this one is going to be having, of course, now the reaction is going to be different between this and this. So let us call this one the reaction of a 1 kilogram particle, and then this one we shall call it the reaction of a 3 kilogram particle. So from there, we can every now see that we can resolve this and resolve this. So if we have to resolve this, that's where it's going to be. This would be D cos 45, because this is R 45. Then this will be D sine 45 degrees. Resolving this. Okay, so this one, we can also resolve it this way. This one is going to be 3D cos 45, because that is going to be 45. And then this will be the sine of it. 3D sine 45 degrees. Okay. So because it's the same string, of course we are going to have the same tension. So I'm going to be having T there, and then there, then T there, and also T in there. Now, this one is frictionless because it's smooth. but here we are going to be expecting some friction. Now, where is the acceleration going to be? Because this one is bigger than this, or the weight is weighter than this, it means that this one is going to be pulling. So expect our acceleration to be in this direction there. And so here, this is going where our acceleration is going to be. So our A, which is root 2. This one, our A is root 2 in that direction there, even this is that direction. Okay, so after doing that, because this one is going to be in this direction, we are going to expect friction, which is going to oppose it, which is going to be mu, but the reaction here, R3. The reaction, because friction is based on this reaction. So here we have reaction 3. Okay, so after having all that summary, then we can come. Tension in the spring. Whenever I see that we have friction, we start by getting these reactions. So for 1 kilogram mass, 1 kilogram mass. So it's that our reaction, if we resolve it in that order, perpendicular to the plane, we don't have an acceleration in this direction, so it means this is going to be equal to this. It's going to be equal to V cos 45. I know that's that. V, that's that our V is 10, taking R to be 10 meters per second. So now our R1 here is going to be 10, but you know 45 is 1 over root 2, is the same as root 2 over 2. So our R1 here will be, this is going to give us 5 root 2 newtons, and that will be that. Why? Because we know that cos 45 minus the same as sine 45 equal to 1 over root 2. If you rationalize this, you get root 2 over 2, which is easy to work with. Okay, now this one, we have said our acceleration is in this direction. That's where our acceleration is. I know that always our resultant force will be equal to times A. This is the resultant force equal to the mass times acceleration. So it's that what is pulling us in this direction, first of all, is this T. So you have that T, then minus, this one is being opposed by this D sine 45 equaling to the mass is 1 times the acceleration, which is root 2. So it's that this will be T minus 10 into root 2 over 2 equaling to root 2. So it's that our T there is going to be, this is going to be 5. We take to the other side, we shall get 6 root 2 newtons. So we have got the tension in the stream. Okay, so after doing that, we come to now, I think we can every use this space. Oh, we can still use some here. So if you want now to come, we come to the 3 kilogram mass. The 3 kilogram mass. So what is our 3 kilogram mass? First of all, now for it to start, if we resolve the forces like this, because we first get always our R3. So our R3 there, so our R3, there's no, it means that this one is going to be balanced in that direction because there's no acceleration in that. So it's going to be equal to 3 B cos 45. So our R3 will be 3 into 10 into root 2 over 2. So if you pass there, you see by this you should get 1, and then here you shall get 5. So our R3 here is going to be 15 root 2 newtons. And so we are done with that. Now, you see, if we resolve along in our direction of the acceleration there. So in our direction of acceleration, like this, where our acceleration is going to be, our resultant is equal to ma. So our resultant, result is going to be taken in there, is going to be this force here. Okay, because of space, let me use this because I'm saying I'm going to be having. So we are on a 3 kilogram mass. If we resolve in this direction, our A, because that's where our acceleration is. Our resultant force will be equal to MA. Our resultant, what is pushing it in this direction, pulling it in this direction, is a 3D sine 45. Then we have the opposing force, T, first of all, and then we have this friction, which is mu, R3, equaling to the mass, which is 3 times the acceleration, which is root 2. So this would be 3 into 10 into root 2 over 2 minus our tension, which is 6 root 2 minus mu, which we are looking for, the coefficient of friction, then times R3. Our R3 here is 15 root 2 equaling to 3 root 2. Okay, I think we can see we can divide this through by this root 2. Anyway, let me pass. Okay, this is going to be by 215 root 2 minus 6 root 2 minus, when I bring this beside, 3 root 2 equaling to 15 root 2 mu. So that we can ably divide it through by this one can ably ignore it through out. So we have 15 minus 6, that is 8, minus 3, we have 5. Sorry? This is 15 minus 6, we get 9, minus 3, we get 6. So this is 6 equaling 15 mu. So that our mu is going to be by 3, 2, by 3, 5. That would be our mu. That's what we had to do there. Then magnitude and direction of the force exerted by the spring to the pulley. So this was our tension, that was part A. Then this was our part B, and that's part C. So it's that this is our pulley there. If we consider it, we have tension there. We have also tension here. So we have here T and we have T. So we need the resultant out there. So this is our resultant, which we are going to call RT. How do we get the resultant? Remember, this T we have it, and this one we have it. So if we have resolved that, you realize, you can see that our RT, because this is known and this is known, you can look at that as this way. So if I make that, I'm going to be having this T like that, because this one is going to this direction. Then I bring it here like this. If this is, I wanted to bring this, then I want to make this one to be part of this. I want to make it look parallel. Or if I this two, or from here, you can able see that this one is going to be the same as this is our RT. So this one can be like this, then like this. And this is our 9. So this is going to be our T. This one is going to be our T, which is 6 root 2, and this is 6 root 2. Our resultant, our RT, is going to be equaling to 6 root 2 squared plus 6 root 2 squared, which will be this times 272 plus 72. So our R2 is going to be 12 newtons. So that's the resultant. This tension is going to apply that. Okay, in simple terms, the magnitude, the resultant, because the force applied by this and this is going to be the same as that of the resultant. This force This first here is equal to the sum of these two. So that's why we have it there like that. So, and the direction where is it going to occur? So it's going to occur downwards. Downwards, so that's the direction. So, that's how we had to take on that question. Now, next lesson we are going to see when these two planes are rough. But please don't forget to subscribe to the channel. Wish you well.